Before we charge off into doing confidence intervals and hypothesis testing, we really want to set up several general concepts here that are going to be crucial to why we do what we do, where it's all coming from, and it'll save us time later, even though right now it may seem a little theoretical. We're going to do it, though, a little bit with the context of a specific problem, and we'll take a look at, say, a material and its tensile strength. And we have some idea that it comes from a normal distribution with, of course, its corresponding parameters of the mean of, in this case, 42 KSI. That's kips per square inch. Remember, kip is 1,000 pounds. And its standard deviation of 8 KSI. And a common situation is that we have randomly pulled out 25 coupons, and we want to ask the question, before we actually conduct the test, what's the likelihood that our sample mean is going to be less than 36 KSI? Now, I chose that specific set of numbers because there is a particular metal out there where we use the yield strength in our calculations as 36 KSI, and these are the properties of the distribution that commonly go along with that. And so the broader question that we're after is something about understanding what the distribution is associated with this thing called a statistics. In this case, this is a sample mean, but we haven't really defined just exactly what is a statistic, and that is that it's anything that is a function of observations in a random sample. So, of course, we have, as one example, we've got the sample mean, there's the sample variance, there's the sample standard deviation, there's the mode, there's the median, kurtosis, coefficient of skewness, etc., etc., etc. One we haven't really introduced much, but is very common out there, is the proportion of a population. Seems like with endless election cycles, we see the polls all the time, literally all the time, about proportion of the population that favors any particular candidate, but there's a broader application here too. Say the proportion of vehicle owners in a foreign market that drives a domestic vehicle, etc., etc., that sort of thing. So this can be very useful and very important for certain business contexts. Right? And along with this idea of, well, here are these various statistics that we can calculate from a given random sample, is that we're interested in how those are distributed, in this notion of what we call a sampling distribution, which is just the probability distribution of a statistic, and of course it's various parameters, whether that's the mean and the variance of that specific thing. So let's look at a specific case, and that being the probability distribution of our sample mean. This will help us to answer this question that I posed up here above, the likelihood that the sample mean, the average of those 25 samples, is going to be less than 36 KSI. And so one of the things that we might look at as we try to address this question of the probability distribution of the sample mean is, well, what should we expect its value to be? And we're going to work through this in all its little full glory and detail. Sometimes the way to do this is just to simply substitute in an expression. We have defined that x bar is equal to the numerical average of all of those observations. Sum of x divided by n, total number, right? And of course we know we can pull a constant out, of that, and we also know that by the linearity operator we can swap the sum and the expected values. So I'll do two steps at once. And because these are independent and identically distributed random variables, that means that these all have the same mean, and we'll have n of those because that's where the sum goes to. So we'll have n mu over n. N cancels out. That is equal to mu. Now keep note, please, that these are not the same quantities. That mu of x bar equal to mu, that these are not by definition the same thing. This is the mean of the sample average, and that happens to equal the parameter mean of the overall population distribution. That's a good thing here. We like that. But these are not fundamentally, these are two different things that we've written down here. That's a crucial kind of idea to keep in mind. The other thing we might be interested in here is, well, what's the variance of the average? And in that case, I want to adopt the terminology symbol of the book and use this capital V for the variance operator of x bar, because it makes it a little easier to get to what our answer is going to be. Right, and so once again, I'll just substitute in directly a definition. And then note that when a variance of a constant times something is the constant squared times the variance of the stuff that's inside. And remember from our joint probability module that this variance of a sum is going to be then the double summation of all of the covariances of the xi and xj's. Right, now, that's the generalized statement, but when we apply our independent, identically distributed identity here, that's going to tell us that the covariance of xi and xj is going to be equal to 0 when I is not equal to j. In other words, we don't have the mix. There's no correlation here between these. And so that simplifies this quite a bit. And since all we're going to be left over with is the covariance when those two are equal to each other, that's just equal to the variance of xi, and those are all the same, right? That goes back to the population measure, right? So we're going to end up with, in this sum, right, now we only have, the only thing that's left when we do the double sum, right, we're going to get rid of all those, all the I not equal to j, so we're only going to have n of these left. Right, so this will be n times sigma squared over n squared. Now, if you get lost in somewhere in that math, note that your textbook goes through the same derivation, and so I did it slightly differently than they did, and so take a look if you want to see how they did it. And so we're left with then that, okay, the variance of the sample mean is equal to the variance of the underlying population divided by n. And that's a pretty important little thing that just ended up showing up here. Both of these are important. We're going to come back to this later and talk about bias. For now, though, let's talk a little bit about what this is really telling us. That notice, as n gets large, then the variance of the sample mean gets small. Right? And let's draw this in a probability kind of sense. We'll have two different probability density functions that we're going to write. And we're plotting here sample mean. One where n is small and one where n is large. Right, in both cases, x bar is going to be centered right on the mean. And so they're centered on the mean, and for a reason why you'll see in a moment that maybe you can already anticipate, I'm going to draw a bell curve here. When n is small, this might be pretty broad, right? Because n small, this variance will start to get large. Compared to when n is large, this variance gets much smaller. So we skinny this thing on up. So when n is getting large, what that's also really telling us here ultimately is that our sample statistics, right? Yeah, the expected value of the sample statistic is equal to the population parameter, right? But if we get n really, really large just in one single shot, then the observed sample mean is going to be much, much, much closer to the true mean than if the n is small. Because remember, even when we take n equal to, say, 100, that's just one data point on this thing here, right? Then we go do n equal to 90, n equal, you do this over and over and over, rather, and you could do this in a controlled way. One day you could sample 100 people's weight, random people, right? And that would give you an average weight. Then the next day you do that again, another 100 people, right? And then you'll have another data point on here. And then you can draw, ultimately you do this for a whole bunch of days, you can start to get a histogram of the sample average, right? Which in itself comes from 100 people, right? And now there's an interesting question. Is n large or is n small? And why did I say this, draw this as a probability distribution that was normal-like, and say, well, we'd see in a moment why that would be the case. Well, we can go right back to our central limit theorem really to demonstrate that, right? As n gets large, we know by the central limit theorem that anything that's representative of a sum, that it becomes normal. And likewise, if we transform that, say, through the typical standard z variable, here's their random variable, x bar, minus its mean divided by its standard deviation. And now when we substitute in, look what happens. We have x bar minus now the mean of the population divided by what we were finding out up here, which now becomes sigma divided by the square root of n. This is a crucial statistic that we have here. That just like x bar is a statistic, it's a random variable, so does then z become a statistic as well. And of two sort of fundamental questions that we might be asking, one of them is going to be, how large is large? The answer there is typically n greater than or equal to 30 tends to be large, possibly 20 depending on the underlying distribution that's at work. But 20 actually works pretty well as a rule of thumb, but 30 almost for sure. Okay? And what happens if we don't know our standard deviation? Right? Commonly what we do is we let our variance equal our sample variance, and that leads us to the t-distribution when we do that. And there again, the difference between n being 20 and 30 will have a potential impact for us. So you ask, wait, what about that question you asked before of the material strength, where we came from a normal distribution, we were going to sample 25, and we were asking the question, what's the likelihood that the sample mean is less than or equal to 36 KSI? How should we then approach that? Well, great, let's go after it. Right? That even if the tensile strength wasn't normal, but it had these two different parameters, the sampling statistic, that being the sample mean, is approximately normal, and with n equal to 25, almost it's a great approximation, if not right there already. Okay, so we can treat x bar as normal with its own mean and standard deviation. And so we know that the expected value of the sample mean is equal to the population, so that's that equals 42 KSI, and its standard deviation is going to be equal to the standard deviation of the population divided by the square root of n, and so that will be 8 divided by the square root of 25, or 8 divided by 5, and that's 1.6 KSI. So that's our first step, and then our second step is going to be then just to go do the normal calculation that the probability that x bar is less than 36 is going to be equal to the probability that z is less than x bar minus its mean divided by the standard deviation of 1.6, right? And so that's going to be the cumulative normal distribution of z less than, and we got to put in our 36, right? Well, actually, that should be z equal to that, and so that is cumulative normal of minus 3.75. That's a really large negative z value, and when you look that up in the normal table, you find out a really small number, 0.4088. That's a real small likelihood that the sample mean is less than 36 KSI. It's key that you understand that we're talking about the sample mean. We're not talking about what would be the likelihood that we pulled out one sample and it was less than or equal to 36 KSI. We're looking at the sample mean, and that's a two totally different kinds of questions. Of course, you could kind of say, well, if I put n equal to 1 in here, I get sigma over square root of 1. Oh, it'd be the same. All right, so it wouldn't be the same z value anymore. All right, this would be a much different kind of number. All right, so there's a much higher likelihood that an individual sample is less than 36 KSI, but there's an exceptionally small that with 25 in our sample size, 25, that the sample average is small. And that tells you actually a lot of information, because if you were to pull out 25, run the test, and you came up with a sample average that was less than 36, that there would be a real strong indicator that something's not right. And either there's a process that is off, there's been a calculation mistake, or there's maybe our understanding of what the true mean and the true standard deviation are somehow in error. All of those come into play, that there is something wrong if we find that out. So this was an intentionally chosen as a low number to get this kind of thing to illustrate this. This is pretty far away, right? It's 1.6 standard deviations away from the sample mean, right? Sorry, let me rephrase that. It is the sample the standard deviation of the sample mean is 1.6 KSI, and this number is many multiples. It's 3.75. It's pretty far away from that. So we should expect this to be this way. We have just a couple more concepts before we conclude this module. One of them is associated with bias. And in our current social culture, the notion of bias is usually considered as a negative kind of thing. And typically, that might be carried over in the mathematical kind of realm as well. I say that it's just sort of a campy way of moving into this topic. First, let's just use this formal notation that a big theta, which is a parameter, and a hat, meaning, okay, here's a point estimator. Of some parameter theta, right? And so if we take a look at the expected value of our point estimator, and it turns out that that is equal to our population parameter, then we have an unbiased estimator. Right, if not, if there's a difference, right, and that's not equal to 0, then we have the bias. And that's the definition in the numerical measure of bias over here. So if we go back and we look at the expected value of our sample mean, it was equal to the mean, so therefore x bar is an unbiased estimator of mu. Now, it's not the only unbiased estimator. There are other ways to get there, and the textbook talks about the median and talks about the trimmed mean, and there's unbiased is not the exclusive sole property that we're after. There's multiple ways to get unbiased estimators of a specific parameter. Let's look at the expected value of the sample variance. Right, that seems goofy to have that written in quite that kind of fashion, but remember that's just expected value of s squared. And remember that s squared was, in our definition, equal to the sum of the xi's minus sample mean quantity squared over, and this was the key, not n, but rather n minus 1. Right, and what the book is going to show you and work out in detail, we're not going to here. So left for the reader to do a casual study of, right? And what we find out, though, is that the expected value of the sample variance is equal to the variance. If we had used n here, that would be something different, and we'd have a biased. So that's why we use this n minus 1 in many cases. But you know, when n is large, there's very little difference between the n minus 1 version and the version that's associated with n. Now remember, we're looking at these statistics as random variables themselves, right? After you have the sampling, they're known, and they're not a random variable anymore. But before we've done the sampling, they are. And remember that for our sample mean, its expected value was equal to the population parameter, but its variance was equal to the population variance divided by n. Right? This is the variance version, not the standard deviation version. Right? And this notion of the variance of the point estimator is important as we get into the next kind of ideas, because X bar is not the only unbiased estimator of the mean. There's other approaches out there that are also unbiased. So what we might consider looking at is that we're looking at a specific parameter theta, and if we have more than one measure that's unbiased, meaning its mean is centered on our population parameter, the one that we probably are going to like better is one that has the smaller variance. Right? So and you might call this, say, theta 1, and this one theta 2. Right? And so the one that has the smallest variance of these would be the MVUE, right, which is the min variance of the unbiased estimator. And so we like that, and you'll see the textbook using this abbreviation quite frequently. Just a couple of more definitions to work through here. The standard error associated with a point estimator is given to us by its standard deviation, or the square root of its variance. Right, so for instance, for our sample mean, the standard error of the sample mean turns out to be sigma over the square root of n, and that was equal to 1.6 KSI for our materials example. Right, and that's a useful number that you'll see reported quite often. It's the standard error of the estimator if it turns out that we don't know sigma, and that oftentimes is the case. Then we oftentimes use our sample standard deviation, in which case now this is going to be equal to s over the square root of n, and that's the estimated standard error. And your textbook goes through an example like that. And in addition to that, then they also talk about the mean squared error or the MSE of an estimator. And that's defined as equal to the expected value of theta, our statistic, minus population parameter squared. Sorry, no, it's not. I need you, production team, to cut out, stop the tape, and get that part out of there. I don't know where the squared happens. Mean squared error. Yes, it is. Production team, if you're still with me, double checked, and I was right. I was only wrong that I questioned myself. So that means you can actually go back and keep that and trim that. That was the end. So I'm assuming you can do that. If not, just stop right there. It's no big deal because we're not going to use that mean squared error thing for a long time, so we can leave that off. I'll redefine it when we get to it in later chapters.